This content is produced by DarkNetBreaker, a cybersecurity and dark web education brand. All videos, posts, and content are strictly for educational and awareness purposes only. We do not promote, support, or encourage any illegal activity. Our mission is to expose digital threats, protect online users, and educate the public about cybersecurity risks in the modern world. Stay ethical. Stay protected.
To move a packet of data efficiently across the globe, the internet requires that routing metadata be visible to every server along the path. Each router needs to know exactly where that data originated and where it is destined. In the 1990s, this structural exposure created a lethal vulnerability for U.S. intelligence. If an operative in a hostile nation sent a report back to a home server, any local observer monitoring the network traffic could map the connection directly back to the operative's physical location. In 1995, the U.S. Naval Research Laboratory was tasked with solving this problem. They needed a way to utilize public internet infrastructure while preventing that infrastructure from recording the identities of the people using it. This created a conflict between two opposing requirements: the internet's need for routing efficiency and the military's need for operational secrecy. Solving it meant designing a network that could route data without knowing its true path. A private, military-only network was not a viable solution. If the U.S. Navy were the only entity using a specific encryption protocol, any traffic using that protocol would instantly flag the user as a government agent. Naval Research Lab researchers Cybersyn, Reed, and Goldschlag proposed onion routing as a way to decouple a user's identity from their online activity. The security of this design relied on the volume of the crowd. To hide high-risk military communications, the system required a massive influx of civilian traffic to serve as cover. The U.S. government was forced to release the software to the public to create the very noise it needed to hide in. By distributing the tools for anonymous communication to protect its own personnel, it provided the technical foundation for the modern dark web. Today, the Tor network operates as an overlay. To navigate it, a user's client first contacts a group of directory authorities to obtain a list of active volunteer relays and their current status. The client software chooses 3 specific relays at random to form a circuit: a guard, a middle, and an exit node. The client establishes a connection with the guard node using a Diffie-Hellman handshake, negotiating a unique session key known only to the user and that specific relay. The client then instructs the guard node to extend the connection to the middle node. A second key is negotiated through the guard, ensuring the guard cannot see the traffic between the user and the middle relay. This process repeats for the exit relay. By the time the circuit is complete, no single node in the chain knows both the sender's origin and the final destination. This 3-hop architecture makes the network infrastructure blind to the data's journey. Trust is distributed across multiple independent actors rather than a single provider. Before the data leaves the user's computer, it is wrapped in 3 layers of encryption, each corresponding to one of the relays in the circuit. As the data passes through the circuit, each relay peels off its specific layer. The guard removes the outer shell, the middle removes the next, and the exit relay peels the final layer to deliver the raw request to the web. To defeat traffic analysis based on packet size, Tor normalizes all data into uniform, fixed-size units of 512 bytes. This uniformity allows the network to support hidden services. By using rendezvous points, a server can host content without ever revealing its physical location or IP address to its visitors. By stripping away identifiable routing data and standardizing packet sizes, Tor removes the primary markers used by traditional network surveillance. Despite its design, Tor is not a perfect shield. Because it utilizes the physical internet, it remains vulnerable to specific types of structural analysis. If an adversary monitors the entry and exit points simultaneously, they can perform a correlation attack. By matching the timing of encrypted traffic entering the network with data exiting it, timing analysis collapses the anonymity, linking the user to the destination. The exit node itself is another point of failure. Since it must remove the final layer of encryption to communicate with the clear web, a malicious operator can log all unencrypted traffic or inject malicious data into the connection. Tor's security model assumes that no single adversary has a global view of the internet. Against an entity with the power to monitor entire continents, the network's trust model breaks down. This architecture also comes with a significant performance cost. Bouncing traffic across 3 random relays around the world creates high latency and reduces total bandwidth. This system was optimized for the clandestine transmission of intelligence data, not the high-speed requirements of modern media or large file transfers. The network's survival relies on its diversity. The presence of millions of daily users, from government agents and dissidents to ordinary citizens, provides the volume of traffic needed to mask individual activities. Tor is a masterclass in defense in depth. It's designed to obscure the sender's identity by using the Internet's own transparency to hide the data's path.